Okay, you are down to the last 2 pages of notes for the whole entire school year, and if you've read the top problem on this page, you will notice that we have finally found the handshake question. So let's think about how this one was different than what we did before. So on the previous page, the first question connected just a diagonal from a single vertex. Okay, so we did just what is evidenced here. So we did a single diagonal. Okay, person reaches across, doesn't reach from side to side. So we can think of it as one person reaches across the group, shakes hands, doesn't shake hands with anybody else. Okay, so it's going to reach across, but doesn't reach side to side, and then we don't address any of the other people. The second thing that we did on the previous page was we said, now everybody's going to reach across, but no one's going to reach side to side. So then we looked at just the diagonals. So we had these people reaching across and these people reaching across, but no one went side to side. On this question, what we're going to have is everyone is going to shake hands with everyone. This is what I would call total connectivity. So now we're not just going to have people reach across, we're actually going to have people reach side to side. So now when we look at our triangle, before we didn't have to really address anything, but now when we look at the triangle, we're going to think about, let's say this person right here is going to shake hands with this person and this person, but then this person right here, well, they've already shaken hands there, they're going to shake hands this way, okay? So what we can see here is now we've got this side to side. So when I'm thinking about how many handshakes for this group, I have 3. So my 3-sided polygon, my triangle, has 3 handshakes. Or 3 people at a party would have 3 handshakes. When I get to the quadrilateral, I of course have this person reaches across. I have this person reaches across. This feels like our second example from before. But then I also have, so there's 2, I also have 3, 4, 5, and 6. So a party with 4 people is going to have 6 handshakes if everyone shakes hands with everybody else one time. Moving on to our pentagon, remember we've got they're reaching across, then we have these ones, then we have these ones. So we have the original diagonals, okay, so we have to add those in, and now we have all of these sides. So you might be catching on to this pattern, so this is going to give us 10. On our last one, again, we've got all the diagonals, so we can draw all of those in, just like we did before. So take a moment to draw in all those diagonals. Oh, I missed one right here. There we go, got them all now. And then we're going to add in the sides. So I've kind of said it subtly so far, but I haven't formally written it down. What we're really doing for this number, for our polygons here, is we're taking our number of diagonals plus our number of sides. So if we take the number of diagonals plus the number of sides, we'll get the total number of handshakes or the total connectivity. So our number of diagonals from the previous page for the hexagon was 9, and then we add in our 6 sides, it gives us 15. Now, just like before, we're going to extend our pattern backwards, okay? We're going to ignore the fact that these numbers aren't going to physically make sense unless you've watched the Muppet movie and you have a me party, okay? Then maybe that would make sense, but we're not going to worry about that. We're going to extend these backwards, but before we can even extend them backwards, we need to think about what's happening here. So my common difference here is a +3 and a +4 and a +5. So the first thing that should be in your head is that this is not linear. The next thing we're going to do is we're going to look at our second difference, and I can see that it's a +1 and a +1. So we can see that this is a quadratic. So this is quadratic, and we need to remember that it's odd. And just like I said before, remember our odd ones are we're going to think like a triangle, okay? Now, let's extend these backwards. So remember, instead of 3, 4, 5, we're going to count backwards. 5, 4, 3, that means this needs to be a +2, and this needs to be a +1. So I need to take 2 away from this, that's going to give me a 1. I need to take 1 away from this, it's going to give me a 0. If I did that right, then this should still be a +1 difference, and this should still be a +1 difference, and it is. So now, since this is a quadratic that's odd, just like before, we're going to double this. Oops. See, look, I even got to demonstrate my awesome erasable pens on here. It's a good day, guys. Okay, so we're going to double all of our patterns. Remember, if we double, we have to undouble or take half of it at the end. So we're going to double it. So we're going to have our 0, we're going to have a 2, we're going to have a 6, we're going to have a 12, a 20, and a 30. Now, you guys might be able to even practice with this one, so we could even pause this video, and if we wanted, we could try to pause it. I'm going to leave that up to Mrs. Twining to decide if she wants to pause that. So remember, but we don't want to really start writing with our 0 here, so we can start writing our numbers. So I'm going to let you kind of start writing them out. Remember, write them low to high. Those of you with a little bit of experience, you're probably cruising through these already. Gotta write these low to high, guys. It'll totally mess you up on the test if you don't. Hint, hint. So I've gotten these all written. If we've done it right, then the first number in each factor pair should create a pattern, which we can see it does. It's increasing by 1, so we're going to go backwards. 5, 4, 3, 2, 1. That means this one needs to be the 0. The second numbers should create a pattern as well. 2, 3, 4, 5, 6. I can take that backwards as well. That's going to give me a 1 right there. So if I did it right, which I'm pretty confident that I did, so if we did it right, this product should give us 0, which it does. So now let's go ahead and think back to our first lesson, and let's write this rule. We know that when we're all done, we're going to have to undouble this or take half of it, so don't forget that. I'm going to write the rule for the first number in each factor pair first. So I can see that they're increasing by 1. So I'm going to have my 1n. 0 minus that common difference is going to give me a -1. Then I'm going to write my linear pattern. It's also increasing by 1, so I have my 1n again. 1 minus 1 is 0, so I'm done. Okay, so now there were 20 people at our party, so we can now figure out how many handshakes were there. So I have my 1/2. 20 minus 1 is 19. That's, of course, 20. And again, we don't need a calculator. Half of 20 is 10. 10 times 19 is 190. There were 190 handshakes. That would be a lot to draw out for us. Okay, so we have 190 handshakes on that. So before we turn the page and we think about working backwards on this, let's summarize the various types of formulas that we have looked at today. So we have total diagonals from one vertex. This was our example number 1. Okay, we developed that formula in example number 1. That was n minus 3. That was one person in the group reaches across, but not side to side, and we only look at a single person. Total diagonals, okay, this was our example 2. This was our 1/2 n, and you can write the products in either order, so I think we wrote it n minus 3 times n on the previous page. Remember, this is everyone in the group reaches across the group and shakes hands, but nobody reaches side to side, okay? And then total connectivity, this is sometimes referred to as pairs of vertices. Pairs of vertices. Sometimes referred to as pairs of vertices or total handshake, so you got to get familiar with that. This was our example 3. And as you can see from up above, that was 1/2 n minus 1 times n. Okay, so those are our formulas, and then we'll stop this, pause it, and then on the next video, we're going to look at how to work backwards on these questions.